18. Okay, good morning everyone again. This is our lecture 18 in high dimensional probability and applications to data science. We're going through these applications to solving hard combinatorial problems. And last time, we considered a difficult problem, an NP-hard problem actually, of maximizing a quadratic form over the Boolean data, 0, 1 data. So given numbers, a, I, j, and this I and j can be, let's say this time, let's make I and j be different. I could be 1 through n, j 1 through m. So given a matrix of numbers, and this matrix, as we seen before, could encode either interactions between atoms or some correlations, or maybe similarities between the points or edges in the graph. So given this structure, given a matrix, we would like to maximize the quadratic form, the sum of aij, xi, let's say yj, over all Boolean xi and yj should be plus or minus 1, let's say. Could be 0, 1, doesn't matter. Plus or minus 1. There are 2 to the n, in this case even 2 to the n times 2 to the m different configurations of xi and yj. And so this is a hard, if you want to solve this problem by checking all of them and then finding the maximizer, that would be too hard, too time consuming, 2 to the n exponential time. So this is a combinatorial program or problem, NP-hard. Okay, so the proposal is to relax this problem to something easier, to a problem that we could actually solve, and that hopefully will be related to the original one. So hopefully there is a back road to the original problem. This time, the relaxation, last time, the relaxation is actually very simple. Instead of xi's and yj's being just numbers, +1 or -1, we let them be now vectors. So both xi's and yi's are allowed to be vectors. If there are numbers, +1 is like this and -1 is like this. They're just one-dimensional vectors that are unit. And now I'm allowing them to point in an arbitrary direction in space, including +1 and -1. So here I'm relaxing this to the sum of aij. And instead of just taking the product of numbers, xi and yj, I'm taking the inner product, scalar product, ui vj. And the maximum is over all vectors in some dimension, let's say in Rd, which are unit vectors. So the norms, the lengths are 1. This is a semi-definite. This can be set up as a semi-definite program. We did a similar job last class using the notion of the Gram matrix. We could do the semi-definite program, and therefore it's convex. And convex problems are generally considered to be tractable. So you can actually put it in the computer and it will solve it in reasonable time. So I'm not saying it's super easy. I'm just saying, okay, tractable, possible. Okay, so that was the proposal. Last time, we realized this proposal for a specific goal for the max cut of the graphs, where there was 1 minus some version of it. And now we're going in full generality and look at this inequality, and we say, is there a back road, right? We want, is there something like the opposite inequality like this? Is this actually, are these problems equivalent to each other? And yes, they are. So the converse, the reverse inequality, is one of the most celebrated results inequalities of the 20th century. It's called Grothendieck's inequality. So for any aij, just like before, and you know what, I'll just copy it from here. So you have that, copy, paste, left-hand side, and I'm copying the other side. Sorry. Paste. And they're equivalent. So this is less than, and then there is a constant, unfortunately. I wish it was 1, but the best known is 1.782 times this. And nobody knows how to improve, at least at this moment. Unbelievable. How can you expect that if you can maximize the quadratic form or any function on the scalars, you automatically get a bound for vectors, even regardless of the dimension. It's in all dimensions, all vectors. Totally beautiful. That's Grothendieck's results, a result of 1953. And the constant is 1979, the best constant. And we'll actually give this proof with the best constant from 1979. The argument is a version of, or the original argument of Grothendieck due to Krivine, a French mathematician. Before we prove this, any questions about the statement, goals? Good.
And how this constant looks like in the closed form?
Yeah, we'll get to it. I can't remember. It's like 2 over pi logarithm of 1 plus root 2, something like that. It has very nice closed form. Yeah, we'll get it. Yeah, anything else? Any other questions? Okay, unbelievable inequality and fantastic proof too. So I think, I don't know, maybe I'm too emotional, but this is like, I think it's what if you like give me 10 proofs of the 20th century, I think this should be one of them, one of the gems in mathematics. Totally, the proof, and it's a gem because it's very non-trivial. It's almost a genius proof that is based on both ingredients for which do not appear in this inequality per se. First is probability, which is not trivial. The inequality is actually deterministic. Yeah, the inequality is actually deterministic. And so there will be probability ingredient. And the probability actually, we already discovered it, as it will be randomized rounding. Here we should not be very surprised after last class about semi-definite programming. Randomized rounding is how we will get from vectors back to scalars. Okay. So here we will use Grothendieck's identity that we proved last time. Expected value of the sign for any 2 vectors. If you pick any 2 vectors, u and v, and we're basically saying what's the probability that the random hyperplane separates them. Okay, so we take 2 vectors and pass like a slice the space with random hyperplane. What's the expected value of separation? So in mathematical forms, it's like you're looking at the signs. The sign will tell you which side of the hyperplane it is, and we kind of prove that this is something like this: 2 over pi arc sine u and v for any 2 unit vectors u and v. the homework actually. In the homework, you're proving this rigorously. Okay, it's a two-dimensional exercise, basically. Trigonometry exercise. Okay, so that's Grothendieck's inequality that we already did last time. It's randomized routing. Okay, perfect. All right, now let's just rethink of what we did last time. What will be the second ingredient? The problem with Grothendieck's inequality is this nonlinearity, the arc sign. That is where we'll lose. Remember last time that we tried to linearize arc sign and put this line instead of that. And once we have the line, everything just falls into the place and we're fine. But this is exactly the place where we lost this arc sign thing. And this time we will do something entirely different. We will not linearize arc sign, but we will use the kernel trick that will take the kernel trick essentially from machine learning to handle this nonlinearity. Without linearizing it, without getting it linear. So these are the two ingredients, and I'll explain now what the kernel trick really means. Instead of trying to fight the arc sign, we will try to find the transformation of these vectors u and v. So we'll find the transformations of u and v, so that after the transformation, I won't have the arc sign on the right-hand side. Okay, so I'm trying to make u and v a little bit different so that this inequality holds without the arc sign in the right-hand side. So I want to find the maps, transformations, let's say phi and psi. Think of them as transformations into a higher dimension. I want to embed everything in a higher dimension, realize this picture in a higher dimension, such that Grothendieck's inequality holds without that nonlinearity. Once we do that, we win. Let's say beta times uv. So now there is no nonlinearity. Beta is just like a proportionality constant. If we can do this, then the normal Grothendieck, okay, sorry. If we can do this, we're done, basically. We'll just repeat the proof of last time, the proof of Gemens-Williamson algorithm. The principal difficulty there was this nonlinearity, and we just linearized, and there it was. So we'll do it this time. Okay. Now let's think if this could be crazy. Is this even possible? Because if that is possible, then the left-hand side, by usual Grothendieck inequality, we know what it is. The left-hand side is 2 over pi arc sine.
It should be Grothendieck identity, yeah.
Sorry,
not
identity. Yeah, exactly. Yeah. By the Grothendieck identity, let me actually highlight this. So that this is our Grothendieck's identity. By the usual Grothendieck identity, this is the left-hand side is arc sine of phi of u, psi of v, and the right-hand side is beta uv. Perfect. So let's move this arc sine to the other side. So it means the inner product of phi of u, psi of v equals, and okay, I multiply by pi over 2, beta pi over 2 uv, and then I take the sine. Okay, I got it. So it's a sine of beta pi over 2 inner product uv. Yeah. Okay. So that is what we are after. this is what we want to have, and this looks like, I know it looks like crazy. So it means that I would like to basically introduce this. I have the original inner product UV. Now I'm doing something very nonlinear to it. Okay, so I'm applying nonlinear transformation, and I'm still hoping to realize that as a usual inner product, but in a different space. Okay, so that is possible. It's called the kernel trick. I'll explain how to do this, but it's really something that should not be very trivial to think, right? We have inner product. Let me tell you guys. So we have usual inner product on our N, on our D, right? And then if I tell you, can we make a different inner product that is, let's say, 5 times the original one? Yeah, of course we can. Just multiply all vectors by √5. You get the new inner product, which, yeah, that's our transformation. Can we make the new inner product that's 10 times that? Yeah, multiply by √10. That's fine. You can do that. But can you make a new inner product that's actually the square of the original one, like UV and then all squared? Then you just, what? How can this is a nonlinear? Inner product should be linear. This is quadratic. It doesn't add up, right? But in fact, we can, and that's called the kernel trick. Very powerful technique, and we will do that. So most of this class will be on this idea of kernel trick, of how to actually make very strange, very arbitrary. In fact, we can make arbitrary nonlinearities here, not just a sign. And we will proceed in little steps. So first, we will make the square. So instead of sine, I'll just make UV squared. I will build up that. Then we will work a little harder and we'll build any monomial, so such as UV to the 10th power. Okay, we'll do that. Once we have all the monomials, we'll add them up. Then we can handle any polynomial. Right? Once we can handle polynomial, we can take the limit and get the Taylor expansion of any function. And that's how we get any nonlinearity. So just building these little blocks will take us there. Okay. Okay. To build that, the building this construction is based on tensors, on tensor calculus. And I'll explain what it is in a very simple way. You shouldn't be afraid. This is not differential geometry, tensor calculus. It's a different one. It's a very simple one. So okay, let's build the square first. So if U is a vector, then we just multiply tensor by itself. So the tensor product of vector with itself, U tensor U, is just a matrix U with entries UI, UJ. Square matrix, UI, UJ. In matrix forms, it's UU transpose. You just multiply entry by entry, you get all the matrix. It now has n squared entries. The original vector has n, now we have n squared. And we equip the space, we look with the usual inner product. With the usual inner product. So Rn squared with the usual inner product. Okay, so how does it work? U tensor U, let's say V tensor V. Let's take the inner product of these two. What's the usual inner product? Well, there's n square entry, so I go from 1 to n, double sum, UI uj, that's entry of U tensor U, VI Vj, that's then the entry of V tensor V. It's a double sum, right? So but the sum separates. I goes into one place, I's like this, V's goes to the other place, J's goes to U, J, Vj. And in fact, each of them is the same. It's like the inner product of U and V. So the result is UV squared. Yeah, you get it. Yeah. So easy peasy, we get it. We get a map phi from Rn into Rn squared such that phi of u, phi of v, inner product, equals the original inner product squared. And the map, of course, is just making the tensor product of u with itself. That's it. Yeah, cool. Okay, that's how we can realize actually the square of the original inner product in a higher dimensional space as a usual inner product in the higher dimensional space. Perfect. Well, now you can guess how to get the inner product cubed, right? I'm pretty sure. We multiply it twice. If you multiply 3 times, you get the cube. So similarly, u tensor u is defined as not a matrix anymore, but it's like a cube, like 3 by 2, n by n by n. So it's ui, uj, uk. It's an array, 3-dimensional array. So now we have n cubed entries here. And then we can keep going. You can keep the 4th power and the 5th power and the general notation. Maybe let's make it this way, tensor k. N to the k way array. And we do exactly the same as before with the square. And we get the map. There is a map phi from Rn into a much higher dimensional space, R to the nk. That realizes the kth power of the kth power of the original inner product as the usual inner product in a higher dimensional space. And the map is easy. Phi of u is just take the kth tensor power. Good. Yeah, your guys are good. Everything explains okay. So far, so good. Yeah. Cool. So we build the square first. Now we build the monomial, any monomial. Remember the ultimate goal. We want to build something like a sine or arbitrary nonlinearity. So we start with a square, easy. Now we get to any monomial. Now we'll sum monomials and we get any polynomial. 3. Okay, so how do we sum monomials? Here we don't. Okay, let's think. The tensor product is used to create just the powers, the products of the inner. And now we have to create sums. And it's going to be not the tensor product, but it will be the sum. In this case, a direct sum. So the direct sum of 2 vectors, u and v. Let's say they can live in different dimensions. Is you just concatenate these 2 strings. You put u and then you add v to it, and a long vector is called the direct sum. Right? So you first list the coordinates of u, and then you list the coordinates of v. The concatenation of these 2 strings. It lives obviously in dimension Rn plus m, n plus m. And you can do the similar job for different vectors and so on and so forth. Many direct products. Good. Okay, now it should be obvious, I think, and let me know if it is not, that if you take direct sums and then you take their inner product, then what happens? just do this coordinate by coordinate, and you get u. Actually, let's try this out. So it's this first sum is with the first sum multiplies the coordinates of u with the coordinates of x, xi, and then as we go down, it multiplies the coordinates of v with the coordinates of y, I guess. And so we get ux plus vy. Yeah, good. So the purpose of this simple exercise is just to show how we can add different things together, add the inner products together, just by concatenation, by direct sum. Excellent. So let's okay. You know what? Let's make an exercise. Let's say someone asks us to find a map, to find a transformation, and we would like to realize that realizes the following thing. I don't know, I'm just making this up, but 2uv, maybe the original one, plus 3uv squared plus 5uv cubed. Okay, so what do we do? Let's see. Phi of u. So I guess it will be two direct sums. It will be something, 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 plus something, something, plus something, something, something. Each sum is each component will realize the corresponding inner product. So for the first one, what should I put here?
Just 2 as a one-dimensional vector.
Yeah, 2 what? Just 2, or just 2. Oh, you'll forget 2.
Everything one-dimensional vector.
Yeah, forget 2. Let's say no 2 for now. Just uv. So then what do we put there as the first component? U.
Just u.
Yeah, exactly. Just u, because then phi of v would be v plus something something, and as you take the inner product, you'll immediately get uv, right? Yeah, so you'll put u. Now, if let's now recreate 2. I gave up. Okay, 2. Then instead of u, I should put root 2. So that phi of v will also be root 2, and then root 2 times root 2 will give me 2. Yeah. So root 2u. Agreed? Yeah, I just want to.
But we allowed like choose phi and psi difference, so we can put phi of u is 2u and psi of u. Psi of v is just phi.
I slipped. It should be phi.
Oh, okay. Mm-hmm.
Yeah. Yeah, then we want to, in this case, it should be the same. Yeah, so root 2. Okay, second component. Now we want to create 3uv squared. So what do we put there? For 3, I guess it should be obvious that we should put something root 3, so it multiplies, gets 3. And then what? Root 3?
Tensor square of u.
Yeah, exactly. That's how we created. That's how we created the square. Remember this? We just take the inner product of u with itself. So we should put u tensor u. Let me do it like this. And phi of v would be obviously v tensor v. So when we take the inner product, we get v squared. Okay. Plus, and this should be now obvious. It should be root 5 u tensor u tensor u. And here's will be v. And we easy to see from just tensor product. If we take the inner product, we get the exact form that we need. Okay. All right, this is our map. It takes us from dimension n to a much higher dimension, which is n plus n squared plus n cubed. But maybe we don't care about the dimension this time. Yep. Okay, built it. Good. So what's the summary? At this point, we can build any polynomial. Any polynomial at all or not?
With positive coefficients.
With positive coefficients, exactly. With non-negative coefficients. Any polynomial with negative coefficients we can do. Good. All right. Unfortunately, if you think of the original nonlinearity that we're targeting here, the sign, it does have negative coefficients of the Taylor expansion. So we're not there yet. So how do we handle negative coefficients? And is it possible even? Is it possible to realize minus UV, for example? It's a simple question. What do you think? Is it possible to do this?
In such form, not, but if we have like different fields psi, then yes.
Yeah, exactly. In this form, not, because if you take u equal v, then the left-hand side is positive. It's an inner product, and the right-hand side is negative, and that's impossible. So not possible. But yeah, so Evgeny, I think, said that. That's right. So we at this point we'll just realize it with two different phis. Let's say one is phi and the other is psi. So how do we do that? We'll just stick signs into the psi. Okay, so for, let's say, example, I would like to realize phi and psi different. Suppose I want the same thing, but with -3 uv squared and -5 uv cubed. Can we do that? So this we can do, right? So we can leave phi the same, just like that. And for psi, we can just put the negative signs where they are needed. And they are needed for -√3. And they are needed for -√5. Should be v, of course, here. V, tensor v, tensor v. Cool. Okay, that's consistent with our original goal. So remember, our original kind of our light at the end of the tunnel is to produce phi and psi to realize the sign nonlinearity. We're getting close. We're getting close. We can now realize any polynomial. So any polynomial. Any polynomial is okay. I can build it in higher dimension. Perfect. Good. Questions? So good? Okay, perfect. Let's think of what exactly we need there. We want to realize the sign. Perfect. What else do we need? Sign. Grothendieck's identity holds for unit vectors. So we would want to make phi of u and psi of v unit vectors. So in addition, for these maps to just map into high dimensions, we would like them to map unit vectors to unit vectors, because we would like to apply this Grothendieck's identity. So we need to keep track of the norms. Let's just check in this exercise. So a little remark. Let's check in this exercise whether that is true. So remark. let's say if we have a unit vector u, what would be the, how does it change the length here? Phi of u, psi of v, psi of u will be the same, of course. It's only the sign is different. All right, let's look at this. What's this norm? Let's actually backtrack a little bit. What's the norm even when we build a square? So we build the square here by this map. What is the norm of u tensor u? The Euclidean norm. If u is a unit vector, what's the norm of u tensor u? Even from here, you can see. Just take u equal v. So on the left, you'll have the norm of phi of u squared, which we want. On the right, you'd have u squared, which is 1. Right? So the norm of u tensor u is 1. If the norm of u is 1, the norm tensor u is 1. So that's okay. So this means that if u is unit, then this norm of u is 1, norm of u tensor u is 1, norm of u tensor u is 1. Everything is 1, except it's, of course, it's multiplied by this weights. So we'll get 2 plus 3, root 2 squared plus root 3 squared plus root 5 squared. 10. Agreed? Okay, so it's not 1, but we want it to be 1. We want to take unit vectors to unit vectors. In this case, it's not working, but let's just keep track of that. Okay, perfect. We built any polynomial now. Now take the limit and take the Taylor expansion. And now we can build any nonlinearity just by expanding it as in Taylor series and taking the limits, right? Because Taylor series gives you polynomials. And so let's just record this proposition. Any function that can be written as Taylor series, and the technical term for this is real analytic. Any real analytic function, f of x, which means that the function of this form we can build two maps, embed this picture in a higher dimensional space in order to realize this nonlinearity uv, like this, for any u and v.
May I ask?
Sure, yeah. Yes, you can. Go ahead.
In this equation, you mean like approximation, or like capital N may be infinity?
Yeah, you're right. Yeah, we should take infinity. Yeah. I don't know what that means, though, right? Do we? Yeah. Okay. Nah.
Maybe it's okay. Like it's mapped to the Hilbert space. Something.
Exactly. It's going to be the Hilbert space. It's going to be not Rn for finite n, but it will be the space of sequences. And space of, yeah, I should have. That's right. That's a good point. So if you know what it is, it's little L2, and that's just the infinite dimensional version of Rn. It's really the space of sequences with the Euclidean norm on them. So yeah, good point. Yeah. That, and moreover, we can keep track of the norms. Phi of, so for any unit vector, for any unit vector u, phi of u squared and psi of u squared. Let's just see, how did we do this? When we build this particular function, what did we get as a norm? We just get the sum of the coefficients, 2 plus 3 plus 5, right? But without the signs, just absolute values, right? So it, and of course, the same happens generally. So sum of k, 0 to infinity, ck, sum of the coefficients of the Taylor expansion. So that's it. Okay, you guys are good? Okay, this class is a little bit more technical and packed, but that's okay. We're like 5 minutes away from the complete proof of Grothendieck's identity. This is the tool that we built. It's a custom-made chainsaw that we now have in our hands, and we can build any nonlinearity whatsoever. In particular, the sign nonlinearity. And let's do that. Let's build the sign nonlinearity. Okay, let's go back here. What is it that we need? We need this. Let me move it, copy. So now we have this tool, we have the chainsaw, and we have this thing. We want to build that. So proposition, I'll just say that we can do this, okay? So there are phi and psi, Rn. This time, I really want to take unit vectors to unit vectors, not 10, right? So this time we do not want to see the 10 here. We really want 1, and that's because the Grothendieck's identity will be applied for that. So there are maps that take unit vectors to unit vectors, and they build this nonlinearity. Phi of u, psi of v is the sign of beta pi over 2 uv. And the beta, we will choose beta to achieve the unit vector here. Beta is our parameter. It's clear that depending on the beta, there will be different Taylor expansions, and there will be different sums. So this will be different, and I will want this to be 1, and we will make beta to be that. So where beta equals, and we'll compute it now from the proof. Okay, so we'll just use this. We'll use our tool, the very powerful tool here, for the specific nonlinearity for f of x equals sine of x, where, you know what, let's call this constant c, sine of cx. Sine of cx, okay. Do we remember the Taylor expansion for sine? All right, this looks like Taylor expansion for e to the exponential, but it's okay. It's definitely going to be linear in the beginning because sine goes this way, and then cx cubed, I think, over 3 factorial. That's its second term. Okay, I think. All right. Correct me if I'm wrong, but I think this is the Taylor expansion for sine function. Good. Okay. Now we could just stop there. We could say, okay, this is a function. Take it and go. Proposition works, but we want to make sure that it takes unit vectors to unit vectors, and for that we would like this sum to be 1. Yes. So we would like the sum to be 1. So let's equate it with 1 ck, and it becomes c. First coefficient c, second coefficient is c cubed over 3 factorial. Next is c to the 5 over 5 factorial, c to the 7 over 7 factorial, and so on and so forth. And now we're solving this equation for c. Horrible equation to solve. But the right-hand side is... Okay, are you with me now? You're okay? Yeah, everything is good so far? I just don't want to lose you at this point, because we're really, really close. Okay, so I want to compute the right-hand side in closed form. That series look like the series for exponential, like e to the c, except it misses every second term. The exponential will start with like 1, and then plus c, then plus c to the 4th over 4 factorial. So it misses half terms.
It should be hyperbolic sinus or something.
Yeah,
like
yeah,
that.
exactly. So it would be e to the c. Let's say if I put e to the c, it would have all the terms. If I put e to the minus c, I would have all terms, but the odd terms will switch their signs. So I'll just add this, divide by 2. If you think about the series for e, it will just cancel the negative, even terms.
In this way, we will cancel odd terms.
Odd terms, minus sign, yes. I would like to cancel odd terms, even terms, yes. Yeah, this is hyperbolic sign. Exactly. All right, this we could solve, right? I equate it with 1, and then this is actually a quadratic equation in e to the c. So I actually did this offline. I'll not bore you with solving quadratic equations. So we solve this, and c, it becomes logarithm of 1 plus root 2. And remember what c was. C is actually beta pi over 2. So this is beta pi over 2. And from this, we recover beta. So beta is 2 over pi log of 1 plus root 2. Whatever it is, some funny number. So I am putting it in the proposition. And now we're done. Yay! So we did this. We built a nonlinearity. Realized a very, very nonlinear function of the inner product as a true inner product in a higher dimension. In explicit form, even beta is explicit, everything is super explicit. Okay, good. All right, we built that. And now that's basically it. So why did we do that even? What did we want? Well, we wanted this, right? Let me backtrack here. So we wanted this because we want the Grothendieck inequality without the sign, without the arc sign here, but with some transformation. So I'll copy this from here, copy. Yeah. And paste it here. Great. So this is what we did. So by page 1, we get this. All right. So proof of Grothendieck's inequality. Grothendieck inequality. Now all this randomized routing is so much simple because it doesn't have the code, this arc sign thing. Okay. So what do we want? We want to bound the quadratic form like this, ui vj, for any unit vectors, ui and vj. That's our goal. Okay, cool. So we use this, we use our tool, and we realize the inner product as expected value of the sign phi of ui, g psi of Vj G. G is a normal random vector. Yeah. Now we don't really care what these are. Let's call this xi. Oh, sine. Sorry, I forgot the sign. Signum. Here, sine. Yeah, and we don't care. Let's call this what xi's and yj's. And they're labels, they're plus or minus ones. That's what we wanted, didn't we? So this is 1 over beta. I can take expectation out by linearity. And we get aij, xi, yj. Perfect. And this is for random xi and yj that are defined this way. But of course, it's less than we can bound it by the maximum of all possible plus or minus ones. Xi, yj. Is this step clear? Yeah. Here we have specific xi's and yj's. And of course, we can only increase the maximum if maximize over all possible xi's and yj's. And that's it. Yay. This is it. This is Grothendieck's identity. We want to bound this maximum of this actually by this, where beta, now 1 over beta is, let's see, beta was this. So 1 over beta is then just the reciprocal pi over 2 log 1 plus root 2. And I put it in my calculator and it gets me 1.782. So that's a closed form of that constant. UED. Quad error demonstrandum. So done. Any questions on this?
Can you please explain? We constructed phi and psi like from finite dimensional to unfinite dimensional, and now we just take
oh yeah,
inner product in which space and what is J in this case, because J was like a vector and now it's like a vector in the infinite dimensional space.
When you know what, you're right. I did not do this properly. You're right. It's phi and psi. They take you from Rn into infinite dimensional space, in fact. And so we have to be careful here. Yeah, right. So instead of doing this, the proper way of doing this is this. First, we define the infinite dimensional version of Rn. And that's L2. L2 is the space of sequences. So U is in L2. If U is a sequence, U1, U2, never ends. And the norm is just a usual kind of Euclidean norm, U1 squared plus U2 squared plus and so on and so forth. But we require that it converges. It's a series now. So this way we build infinite dimensional version of Rn. And that is called the sequence space L2. It is a Hilbert space with the inner product UV, which is U1 V1 plus U2 V2 plus etc. Again, converges. So that would be the proper way to do this, is to actually don't restrict the dimension, just go immediately into infinite dimensions, L2. Then let's correct this. It's actually a good thing to do. Then I'm correcting this thing. It's not this space. This maps are not taking you into Rn really. They take you into L2, the L2, the infinite dimensional version of it. Everything is okay there. And yeah, then we need this inequality. And for that, we need Grothendieck's identity in L2. Yeah, I think because P of U, yeah. Oh, okay. There's lots of.
And
so we need to define somehow a random vector in L2.
Yeah, like we defined G. What's G in Rn? It's just G1, G2, G3, Gn. Independent normal coordinates. And now we just don't restrict that. We just G1, G2, G3, and they go on and on. So that will be the proper Gaussian vector in L2. Yeah, that's a very good point. And so here, when we talk about Grothendieck's identity, we can't restrict them anymore because we actually will apply this in infinite dimensions. So I should have said this is L2 now, and the G is, and G is a normal vector in infinite dimension, G1, G2, etc.
Is normal vector in L2 like lies in L2? Like does it have finite norm?
Oh, crazy! No, it doesn't. You're right.
And can we avoid altogether this infinite dimension stuff and instead kind of try to, like Evgeny earlier said, that is it equality or approximation? So we can say that for every.
Yeah, Pablo, you're breaking up, but I think I get what you say. Yeah, we can make an approximate.
From the below. Yeah. So.
Yeah, we can make the approximate version of this algorithm in finite dimensions and then just take the limit in the end, numerical limit in the end, or vector limit or something like this. We can do that. Alternatively, a way to correct this without going through this crazy L2 stuff would be let's see, how do I want to say, to note that there are finitely many, to start working in L2, but then note that there's only finitely many vectors that we're caring about. And so we can just restrict ourselves to the span, to the linear span of these vectors, which is finite dimensional, and it can be identified with Rn. So we can fall back onto Rn. So yeah, annoying, I know, but maybe approximation is actually better. Let me think about it. Let's think together about this. Let me know how to best make it without making a lot of mess in the argument. Yeah, it's a very good question. Anything else? Okay, a couple of questions. So this constant in Grothendieck's inequality 1.78 to 2, whatever this log constant called Krivine, Krivine's constant, who basically gave the proof that we gave today. Is it optimal? No, it's not optimal. For many years, like decades, people thought that this is an optimal constant. And it's actually not optimal. It was proved relatively recently by Braverman and collaborators in 2011. Although the proof is kind of existential, it just shows that it could be improved, but it doesn't give you any constructive improvement. Well, maybe it does, but it's like 10 to the minus 20 improvement. Very, very tiny. Oh yeah, and that, and also how to get the solution from the solution UIs of the semi-definite program to the solution of the original problem, so uivj, to the solution of xiyj. This can be done by randomized rounding, by an application of a similar argument, but it's not a little non-trivial. The paper, you can read it, is Alon and Naor. I think it's 2005, maybe. It's kind of a constructive version of this, where you, from uivj vectors, you get labels by randomized rounding. Good. Yeah, that's all. Any questions? Oh, do you know who Grothendieck was? No? Who knows what Grothendieck was? Who heard about Grothendieck at all?
He's a part of Bourbaki?
Or
another one?
No, Dieudonné was, but his collaborator. But no, I don't think Grothendieck was. You'd be surprised. But you're close, actually. Yeah, it was close to the many Bourbaki group members of this group. Yeah. So Grothendieck was one of the most enigmatic personalities, I think, in the mathematics of the 20th century. He started. Okay, let me tell you the story. If you don't want to hear it, you can disconnect. But let me tell you, because he's my kind of personal hero too. He was born in Nazi Germany, I think, or in Germany, actually in Weimar, Germany, 1928 or something like this. And his father was I think, a Jewish origin. And so when Hitler came to power, they emigrated to France. But in France, his mother actually was German. And so in France, they were immediately interned, and they were basically stateless because of the mother's nationality. And so he didn't have any proper background in mathematics or anything like that. He was stateless actually for most of his life. He refused to take French citizenship at some point. And so he didn't have any mathematical background. And then when he was moving from place to place for the internal camps, he started to be interested in mathematics. By himself, he rediscovered Lebesgue measure and Lebesgue integral without knowing anything about it, without knowing that Lebesgue actually did it 10 years ago. But then he started to study, and he was interested in, he was a student of Laurent Schwartz, I think, and he was interested in topological metric spaces and the analysis of that time. And he started solving open problems, but he wasn't really interested in publishing anything. He just okay, just for fun. He was doing this, and then at some point he moved to Brazil. I can't remember because of what, because he didn't want to take French citizenship, I guess. And in Brazil, while working in Brazil in complete isolation, he wrote a huge manuscript called Résumé de Espèces Topologiques, or something like this, of metric products of topological spaces, which people started to call Grothendieck's résumé because of the first letter. And then in that résumé, he proved Grothendieck's inequality that we just proved today. This was result number 1 in his résumé. It went relatively unnoticed, I think, because he published, he didn't care about anything. He just published in the local Brazilian journal, and very few people read anything there. But then he was increasingly more and more interested in very deep questions, and he was trying to prove the existence of a basis in a Banach space, which was a very famous open problem that for any Banach space, any normed space X, any Banach space X, there is a basis, which means that there are sequence V1 through V2 and so on and so forth, so that any vector, any separable Banach space, but if you don't know what it is, it's fine. And for any X, any vector can be uniquely represented, as well, like a basis expansion, AIVI. Only this is infinity, like this. Is it true or not true? That's the question. for any organic spacer is this thing. And Grothendieck, he was very kind of, he was a positivist in his mind. He really believed in results. And this was so elegant and so natural thing that he believed that he would do this, and he could not do this in 5 years. And that almost crushed him. Only later in 1972 did people disprove this conjecture. So there is no, the key word, if you want to look at this, Schauder basis, no Schauder basis. People constructed the first space without the Schauder basis. The first construction was by Enflow in 73. Who was actually both mathematician and a pianist professional at the same time. So yeah, but Grothendieck did not even look at that direction, the negative direction. He wanted to prove things, and that really was a blow, I think, to him. And he then switched to algebraic geometry, to algebra, then increasingly more to algebraic number theory and algebraic geometry. And at that point, he said, well, when I moved to algebraic geometry, it was like a fresh air and like open possibilities, and analysis was so stiff and so on and so forth. And I was working analysis. I was insulted by this. And what is he talking about? Anyway, so that was his thing. He moved to algebraic geometry, again working in relative isolation, and he revolutionized it totally. Like in the 19th century, algebraic geometry was something like Italian people did, this conic varieties. And Grothendieck totally moved the focus into much, much more abstract way of looking at algebraic geometry, including his theory of like a relative point of view, when instead of, if you want to study the structure, you actually want to study not the structure itself, but you study the maps, the automorphic maps on that structure. And so he revolutionized algebraic geometry and moved to France, moved to Paris, and started to work with students. And he published enormous. He was like working day and night. He was almost just all math, making the seminars every day, and published like 500 pages in a year. And this was totally like 4 or 5 years. It's like an Einstein in some sense. So totally here, and then he refused Fields Prize in Moscow, actually. But his political convictions grew more and more radical in the sense he didn't want to do anything that has military funding. And he wanted to participate in political activity very, very openly, and that was 60s now. So we're talking about like Vietnam War and unrests that fractured Sorbonne in Paris, riots in Paris. And he was more and more increasingly involved in that too. So he refused to travel to Moscow because of communism. He refused to take any money from the French government, and that put him in a very uneasy position, because there was no university that could actually hold that promise that no money would come from military, and you can do whatever political activism, and you can publish political. And so he after I think 5 or 6 years in 1970, can't remember, like 77 maybe, he just resigned from everything. He resigned from all posts in France, and he disappeared totally from the scene. Having published everything, revolutionized everything, he disappeared. And when I entered mathematics, it was actually unknown whether Grothendieck was alive or not. He, for 20 years, like who? Like Bradbury, right? That's another personality. Salinger, Bradbury, Salinger, I think, was the one who disappeared. Anyway, so he disappeared, and he lived, and he reappeared, actually. People located him in 2001 or something like this, living in isolation in the Pyrenees. So his story was something like this. In the 60s, let me actually show you this. So this is him in his golden years in France, when he was like publishing 500 pages and making all this big thing. And then in the 60s, when Vietnam War started, he actually moved to Vietnam and was, he's still in France here. This is France. And then he moved to Vietnam, and he was teaching in the jungles and rainforests and trying to teach these people algebraic geometry. And I don't know about the success of that, but that was, he actually he was in the areas of the active bombing there. So he would go where the active bombing is and establish the mathematical school there and just teach them all his version of algebraic geometry. I don't know how successful that was, but it was really a big thing for him. And then he moved back and to France and little village, and he lived there in complete isolation from everything. He continued to publish things, and they're still, actually most of them are still waiting to be deciphered. There's like 1,000 pages manuscript, like Pursuing Stacks, for example, manuscript like this. A Long March Through Galois Theory, 2,000 pages, and all of them are just so. Yeah, and so he then become more like a hermit. First more like a Buddhist version, and then leaning toward Christianity a little bit. But he would starve himself to death, living on dandelion soup, like from grass. But local villagers fed him eventually, so he didn't die immediately. And then he started to write some strange things, which it wasn't clear whether he was sane or not, or what is sanity actually. So very strange things. And yeah, and he died in 2005, I think, 2003, 2005. Yeah, but the guy is totally nuts. It's just he refused all the prizes. He just went in isolation. And yeah. And his arguments are ingenious. I think this Grothendieck's inequality that we just saw. Who would ever think? Where is this? Who would ever think that an inequality like this, which is completely deterministic, right? If you can bound the quadratic form on Boolean data, you can bound it on vectors. Who would think that this inequality, first of all, could hold? I would look at this and I say, no, it's impossible, because the set is so much, in any dimension, so much larger. And second of all, to think of this way of proving it. This is actually what we did is Krivine's argument, but it's very close to Grothendieck in some sense. So this randomized rounding plus the tensor plus the kernel trick, this tensor thing. The kernel trick wasn't available back then, actually, in machine learning. So in fact, maybe Grothendieck discovered it. So he rediscovered kernel trick and he rediscovered randomized rounding, put it together, and you get this inequality. Come on. Yeah, all working by himself in Brazil. Totally. Anyway, so he's my hero. Yeah. Good. Any questions? Great, people. Okay, sounds good. I will try to schedule another guest meeting, and we will be good. And I'll see you all on